Here we are right in the beginning of tornado season, but be careful, tornado season is all year long. No matter what the news tells you, no matter what the public tells you, there really is no beginning and end. There's just a seasonality in the increases and the decreases in the numbers of tornadoes that we have, as well as the strengths and the types of tornadoes that we can see most often, depending on the time of year and where you are across the country. So you've seen this picture probably before. In the early 1990s, this was taken over Lake Okeechobee in Florida. So technically, this is actually a waterspout, but I will get into the differences between tornadoes and waterspouts real soon. This one is actually just a tornado over water. There are differences between real actual waterspouts and tornadoes. Now, the reason I selected this topic is, of course, this time of year. This is actually Tornado Awareness Week. So when they were looking for volunteers to come in and speak for the series this semester, I thought, well, hey, it's a pretty appropriate topic this time of year. Plus, the National Weather Service and the National Atmospheric and Oceanographic Administration has put out some storm spotting classes out there, which some of you might have been at last week in Sheboygan Falls, or you might have been at these in previous years that they've offered them. So I figured, everything was just good timing. But as far as this particular topic, the geographic influences on tornadoes, people don't think of geography really mattering much when it comes to tornadoes. It has everything to do with tornadoes, especially here in the United States. As you see from this world map, we have by far the most tornadoes than anywhere else in the world, by far. I think we have 3/4 or more of the world's tornadoes on an annual basis. This map is showing basically the risk areas, the high and lower risk areas where tornadoes actually occur. As you can see, most of the world doesn't get any at all. And if they do, they're very rare and very low occurring, to the point where they don't even put a shading of color on this map to show that they have any kind of risk at all. But the only dark, high-risk area is in the United States, the eastern 2/3 of our country, and in southern parts of Canada as well. The other areas of the world that have moderate risks, and the next darker shade of purple here, parts of Europe, certain other parts of the world, but by far we have the most, and we also have the most destructive of the severe thunderstorms and severe weather and tornadoes, by far more than anyone else in the world as well. So looking at the physical geography of the United States, physical geography being the earth science part of geography. When people think of geography, they think of countries and capitals and cultures and those types of things. That is certainly part of geography. That is certainly part of human or cultural geography. But we're looking at the physical side, the actual physical landscape and the atmosphere itself, and how they interact and work with each other. So starting basically with our physical geography, we have a very unique setup compared to anywhere else in the world, as far as stark contrasts in different types of air masses and different types of temperature and humidity characteristics, all within a relatively short distance from each other, as far as the dominant climates and the dominant climate characteristics between such a small area. This map is just showing some of the average temperatures throughout the United States throughout the year. And as you can see, within just about 1,000 miles, we change average temperatures about 30 or 40 degrees, which is huge when it comes to the necessities for tornado formation and severe weather formation. We also have a very flat landscape, relatively speaking, a flat landscape, which is also very crucial in the allowance of severe thunderstorm activity to develop. The way that the surface interacts with the atmosphere the atmosphere is very sensitive to abrupt changes in the landscape, i.e. mountains or even smaller mountain ranges for that instance. But we have the eastern 2/3 of our country, basically everything east of the Rocky Mountains is considered flat landscape, minus that small little hump in the land from about Pennsylvania down into Georgia, the Appalachian Mountains. But still a relatively low-lying landscape, and you can still have severe weather and tornadic activity even in higher elevations as such. Getting a little more specific as far as these different temperature regimes as we see throughout the country here. Again, very drastic changes between the northern and the southern part of our country within average temperatures. Throwing seasonality into that, summer, winter temperatures, for instance, changes that dramatically as well, but we'll get into that later. But going a little bit deeper into detail about these temperature characteristics, the most important thing that gives us such a unique, I guess, kind of a unique stage setup for severe weather in our country is the Gulf of Mexico. It is a vast energy source, and by energy I'm not referring to electricity or conductivity or anything like that. I'm referring to warm temperatures and the amount of humidity in the air, the amount of water vapor in the air. The Gulf of Mexico is a very shallow, relatively shallow body of water when it comes to ocean water. This allows it to warm up very quickly, not to mention the fact that it's sitting in a subtropical climate and dominated by high pressure most of the year, which allows lots of sunlight to get through. When you have dominant high pressure, you don't have a lot of cloud formation, so you have clear skies. This allows the sunlight to penetrate this relatively shallow body of water and allows it to warm up tremendously. The warmer of a body of water that you have, especially continental size like this, the larger amounts of evaporation you're going to have and the more humidity you're going to have in this region. And this air mass extends all the way up into the southern United States. So that's our first main geographic component of why we have such a unique setup for severe weather in this country. We also have a very cold air mass to the north, always. Even during our summer season, the differences in air mass characteristics between the southern U.S. and the northern U.S., basically on either side of that jet stream, which I'll get to later, the air mass characteristics are completely different. You're talking about very cool and dry conditions to the north and much warmer and more humid conditions to the south. And it's a result of this large landmass that we have, as well as the Rocky Mountains. The Rocky Mountains with this high elevation allows for cold air to form and basically sit there. And then when certain weather systems move through, it'll bring that cold air to the east, a big key ingredient to severe weather formation. But also the cold air that forms in the northern half of the North American continent. Large land masses are relatively cool and dry compared to anything near water bodies, namely oceans, coastal areas, where you have warmer temperatures, warmer water temperatures evaporating and giving off humidity in the atmosphere. Large inland areas like this don't have naturally occurring large amounts of humidity in the air. So again, cold, cooler and dry air masses to the north and very warm and humid air masses to the south. Getting into air masses in a little more detail. What you see here are generalized locations where you find different types of air masses. And air masses are characterized strictly by temperature and humidity characteristics, as I've been talking about. And the two main ones that we're really concerned with when it comes to severe weather in our country, especially over the eastern 2/3 of the United States, are this maritime tropical air mass, this subtropical high pressure system that sits pretty much in the Gulf of Mexico and the Caribbean year-round. It migrates a little bit north and south throughout the year, during the changes of the seasons and all that, and its extent can be rather confined or it can be rather extensive. It depends again on time of year and other weather factors going on in nearby systems. The other main important one here is is this my pointer? Yay, I do have a laser pointer, all right. Is this continental polar air mass I've been talking about. That is our Canadian and Rockies air mass. Again, much cooler, far less humidity in the air. And it's these starkly contrasting air masses when they come together that provide us with the severe weather that we get so frequently. A third air mass that's important, as we'll get to in a little bit here, is this continental tropical. It's tropical, so it's warm, we know that, but it's continental. And that gives us the idea that of the humidity characteristics of this air mass. Continental air masses are much drier than our maritime air masses, maritime meaning that they're borne over water. Of course, they're going to have more humidity in them because they're evaporating all that water that's underneath them. But a continental tropical is more characterized by more like desert-type climate conditions. Continental, so it's dry, yet it's tropical, so it's very warm still. And that plays a key part in severe weather, especially across the Great Plains, areas of Texas, Oklahoma, Kansas in the spring and summer months. but I will get to that in a little bit here. So it's these three these two especially, the continental polar and the maritime tropical air mass we're most concerned with, but this continental tropical. And you'll hear the term dry line a lot, and that's where that comes from, is from this continental tropical air mass, warm and dry, coming from our southwestern desert area of the US. Now these air masses, the characteristics of the air masses basically develop what we all know as a jet stream. Everybody hears the weathermen talking about the jet stream all the time, but nobody really understands what it is other than it's a river of flowing air in the atmosphere. That's what your meteorologist will tell you all the time. Well, what does that really mean? Or how is this river of air actually flowing, so to speak? If you look at a profile of our atmosphere, we take a chunk of the Earth, half of our Earth, one half dome, and you look at the atmosphere above the actual surface, you will see that the atmosphere goes much higher up in our tropical areas where it's warm. Does anybody know why that would be? Versus where it's very cold, where the cold regions are, the atmosphere is going to be much lower. The top of the atmosphere is going to be much lower than the top of the atmosphere is where it's much warmer. Does anybody know why that would be? Density of the air has a lot to do with it, but what? Warm air, yes. Warm air from the surface rises naturally, as we know. That pushes up the top of our atmosphere much higher than in areas of the world where it's really cold. That atmosphere, that cold air is constantly sinking, so the top of that atmosphere is much lower. The difference between a tropical air mass and its nearby polar air mass, there's a sharp slide in the atmosphere from the top of the atmosphere down into where where the warmer region is into the colder region. So think about that now as a separation. The atmosphere is much higher here and the atmosphere is much lower here. But what is actually causing this and why is it flowing that way? There's a certain thing you'll learn in physical science in high school. It's called the something force. Starts with a C. The Coriolis force, exactly. Winds move basically from high pressure to low pressure. And in the upper atmosphere where it's higher, that's considered higher upper level atmospheric pressure versus the lower upper level atmospheric pressure to the north. So high pressure is going to flow to low pressure in the upper atmosphere. That air is going to slide straight north towards that colder air, right? So why is it flowing this way? The Coriolis force states that in the northern hemisphere, everything that doesn't have any kind of deflection or any kind of friction adding to its direction is going to flow to the right. Everything's going to turn to the right naturally based on the, on the rotation of the Earth itself. So this air wants to push northward, but it's being pushed to the east very rapidly by this Coriolis force, by the natural rotation of the Earth. But what's important about this jet stream now is that, again, it's in the upper atmosphere. It separates where your warmer and colder air masses are, but you also have this rapidly flowing area of winds in the upper atmosphere. And when I get into the development of cyclonic systems or low pressure systems, which is basically where all of our thunderstorms form, the storm tracks follow the path of these jet streams. Now, I talked about these air masses. What our air masses actually are dominant high pressure systems. So this high pressure system you see here sitting over the Gulf of Mexico, that's our subtropical high. That is our maritime tropical air mass. This guy right here, he is our continental polar air mass, dipping down to the south, coming in from the Alberta area. Some of you have probably heard of Alberta clippers before. That idea kind of came from where these systems kind of originate and where they end up flowing to. Then you got this guy right here. This is another air mass here. This is our continental tropical, moving up from the desert southwest, kind of moving up into the Rockies. So our air masses are actually dominant high pressure systems. But how these high pressure systems play out and how they start to form severe weather is that the way that they border each other, you have winds grinding against each other, and that's what spins off these low pressure systems. Let's start with the diagram below here. A here, you see two bordering high pressure systems. High pressure systems are basically areas of surface airflow rotation. In the northern hemisphere, a high pressure system rotates clockwise. So to the south, right here, you have a rotating high pressure system rotating clockwise. Surface winds all the way up, not to too high levels of the atmosphere, but basically our surface winds are generally following a clockwise rotational pattern. Same thing with this high pressure here to the north, this continental polar. Now where they border each other, right here, this cold front here, as you can see, where they border each other, the winds are flowing against each other. So the northern flank of this subtropical high, this northern flank right here, is flowing from west to east, southwest and northeastish, right? The southern flank of the continental polar high pressure is flowing from northeast to southwest. Where they meet, they're flowing against each other. So as you can see in this first diagram here, the first part of the spinning off of a low pressure system, again, the systems that are conducive for rain and for severe weather, the first step is these two grinding against each other and eventually spinning off a low pressure system. I can't get into too much of the details since we only have an hour tonight. This is something my weather and climate class we probably spend about a week on talking about. And I got all these cool interactive labs and everything you could play with. It's really neat. But we don't have time for that tonight, I'm sorry. But generally speaking, where these pressure systems border each other, where the flows are against each other, and you have starkly contrasting, again, air mass characteristics, cold, dense air, warm, very buoyant air, again, kind of coming together, eventually they spin off this low pressure system. This creates this, what's called a wave cyclone or a mid-latitude cyclone. Cyclonic refers to the type of rotation as well. Low pressure is cyclonic. High pressure systems are anticyclonic. I won't refer to them as much as cyclonic systems as much as low and high pressure. But low pressure systems now are rotating counterclockwise. So you get the system spun off from the bordering, the grinding against each other of these two bordering high pressure systems. It creates cold fronts and it creates warm fronts. The warm front of this is sucking in all the warm air from the southwest, that continental tropical air mass, that desert air, that dry air mass, but mostly this this maritime tropical air mass, the very warm and humid air mass. This is what really feeds the storms, and I'll get into how those develop and feed off the humidity from those storms in a bit. Yes?
The barometric pressure on that either rise or fall, or how does it vary?
Actually, different parts of this system, depending on where you are and which way it's moving, certain parts the pressure is falling and certain parts the pressure is rising. Ask me at the end of the presentation and I'll go over this particular slide and I'll tell you where those are. I don't mind interruptions with questions, but I might have to save the full answer till later on, or I might be getting to it in slides to come, just so you know. But where we have the most action now with these low pressure systems, mainly you have the most severe of the thunderstorms along this cold front. This cold front is moving in. As you can see this top diagram here, cold air is very dense and it's going to stay low to the ground. And anything ahead of it that's warmer is going to be pushing that air up into the atmosphere. Warm fronts are different. Warm fronts are moving into the colder area, but warm air does not take over cold air. Warm air is too buoyant and this cold air is too dense to be taken over by it. So for many miles, this warm air slides over the cold air ahead of it. And that is the process that forces up the warm, humid air into the upper part of the atmosphere where it cools and cloud formation and rain formation takes place. And I'll get into those specifics real quick here. But there are two different ways of forcing warm, humid air into the cooler upper part of the atmosphere where the cloud formation and the condensation process takes place. Again, talking about the importance of the continental tropical or the desert, our desert southwest air mass. It can have the same effect as far as lifting warm, humid air up into the atmosphere, higher up into the cooler part of the atmosphere to form clouds and rain and all that. This dry line can have that same effect that a cold front can have. Now, it's warm air. Now, you're talking about, can warm air take over warm air? Yes, it can. Even if it's warmer, a warmer air mass can take over a warm air mass that's not as warm. The warm air mass, the tropical air mass, right over on this side, has a lot of humidity in that, and that makes the air more buoyant. Does anybody know why humid air would be more buoyant than dry air would be? Water vapor has an incredible, water in general has an incredible ability to hold heat and energy. So generally you're going to have not necessarily warmer temperatures, but in all those little tiny little pieces of water vapor that are in the atmosphere, there's a whole hell of a lot of energy stored in just all those little pieces of water vapor alone. So that makes the air, that tends to make the air a little more buoyant and easier to lift versus a denser, drier air mass, whether it's warm or not. But these dry lines, basically the separation boundary between your more desert air mass and your more tropical air mass to the south, this dry line can do the same thing as a cold front can do. It can lift up the warm, humid air ahead of it and cause thunderstorms to develop. You will hear, especially in the spring and summer months, starting right about now, when the storms really start firing up in Texas, Oklahoma, and in those areas, you're going to hear that term dry line a lot, and that's what that is. And here's an example now of these key ingredients and all coming together in a perfect fashion. A lot of times you don't have a dry line, but sometimes you do. And when you have that taking place, you can have almost a double effect or almost a double hazard with this type of cyclonic or this type of low pressure storm system moving through. Okay, just another way of looking at this right now. Again, you can have tornadoes and severe weather forming along the cold front. You can have them forming along the dry line as well. You can have them forming along the warm front too, as we see. There's just a different type of lifting mechanism. Generally, the storms along the warm fronts aren't as severe, but that's generally, they've been known to be pretty severe and produce tornadoes as well. Again, another thing I will be getting to real soon. All right, so what we know now about tornadoes is most people think that they're all the same. They're really not. There's different types. There's 4 different types I'm going to be talking about today. 2 of them are very similar, but the other 2 besides that are quite different. Most of the ones that we know are the ones like this. They form from supercell or mesocyclonic type huge thunderstorms. This is where the warm and the cold air are coming together, and they're coming together in the perfect fashion, and these very powerful and very violent tornadoes develop. That's what we're basically told on the news. That's what the media covers mostly, and that's what you hear about most, because those are the ones that cause the most damage, the most property damage, take the most lives. They're the most severe. You've probably seen a very typical kind of anatomical diagram like this of a supercell or of a mesocyclonic type of thunderstorm. Mesocyclone meaning it's the kind of a large-scale rotation going on inside the cloud. And I'm going to get real soon talking about how that actually develops. But this is what this perfect setup that you normally see. But how do we get to this? How does this actually happen? How does this rotation inside the cloud become inverted and become more vertical, and then become strong enough where the tail end of it dips down and touches the ground, as we see as the tornado? How does this actually happen? A lot of people tell you, well, it's just some rotation in the cloud, and once it gets too strong, then it flips up and the tornado drops out. That's not quite really how it happens. How these storms begin to actually rotate so violently is the upper level winds, as well as the winds as you climb, the different directions of the winds as you're climbing up into the atmosphere. A storm, in its basic sense, starts from the ground heating up. Don't be mistaken. Everybody thinks that another myth. I'm going to be talking about a lot of myths tonight. That I'm going to be busting some myths and dispelling some of the things that we commonly think are true, and they're not. The sun does not heat up our air. The sun does not heat up our atmosphere. It heats up the ground. It heats up the surface of the earth. The surface of the earth heats up and gives off heat and energy. That is trapped in by our atmosphere. The greenhouse effect, you might have heard that before. This increasing greenhouse effect is what's giving us climate change and global warming right now. Increased gases and certain things in the atmosphere which contribute and which help trap in heat and energy in our atmosphere are increasing. As the ground heats up and this warm air starts to rise from the surface, if it's intense enough, if it's a warm enough day, the ground heats up enough, and there's enough rising warm air, it can get up into parts of the atmosphere where it's very cool, and what's called the condensation process takes place. All the water vapor, all the humidity in the air all these little water droplets start to slow down and and bump into each other and stick together. It's a process of collision and coalescence. You might hear your meteorologists talk about that. But this is what gives you cloud formation. Eventually, these water droplets become big enough and gathered enough in localized areas where you can start visibly seeing. You can see the sun bouncing off of it and reflecting this big white cloud. And that's basically just a big collection of small water droplets that are big enough to collect. And when those water droplets get too big and they can't stay suspended in the air anymore, they fall as rain. So really, in the simplest sense, that's how we get rain. And that's how we get cloud formation. But this rising warm air can get up into the atmosphere where the cap of the atmosphere is telling it, I don't want you to rise anymore. I want you to stay put. I want you to stay down there. But there's so much of it, and it's the rising motion is so strong, it starts getting up into the upper part of the atmosphere where it doesn't belong. And the winds that are up there, these upper level winds, our jet stream winds are part of that. They start knocking down this rising warm air. Think of this guy being pushed down is rising warm air, and these winds get stronger as you climb higher up in the atmosphere. There's less surface friction affecting them, so they are blowing more swiftly. So the stronger that these winds get, the higher you go up, the more this bubbling up warm air is being pushed back down. And on large scales, on large regional scales, this creates a type of tube rotation within the cloud itself, and that's what's called the mesocyclone. If it gets intense enough and large enough, it's referred to as a mesocyclone. All storms do this a little bit, but our most violent of thunderstorms are produced by this incredible rotation going on inside these large clouds. So these three diagrams give you another idea here. With this first one on top, what I was just showing you, rising warm air starts to be kind of pushed down by these strong winds aloft, these jet stream winds. And it's not just the jet stream. There's other winds going on the higher up you go in the atmosphere as well, and they keep changing direction, as you can see on this guy right here. But the beginning stages of the actual storm starting to rotate are from these large amounts of big pockets of warm air rising and being pushed back down and being forced to start to rotate. Not only do we have the heat and energy coming off the ground, but as the water vapor in the air starts to condense and form clouds, all the energy that's held inside those water droplets is released. If you remember from physical science in school, there's something called latent heat. So when you take water and you freeze it, you're taking the heat and energy out of the water and causing those water molecules to slow down and stick together and eventually freeze. The opposite with evaporation is that you're adding energy to the water, so you're melting it, or you're taking the water and putting more energy in it eventually to separate those little pieces that come out as water vapor and humidity through evaporation. But with all the evaporation, with all the condensation going on in the upper part of the atmosphere where it's getting cooler and cooler, you're squeezing out all this energy outside, you're squeezing it all out of the water vapor. This essentially is kind of warming up the cloud environment itself. And as I said before, water vapor has an incredible ability to hold heat and energy. It is also the thing that warms up the cloud and allows the cloud to hold more water vapor. The warmer the temperatures, the more water vapor, the more humidity the atmosphere can hold. So as you're warming up this cloud environment, it allows it to basically feed off and grow itself based on the processes that are going on within. And this further destabilizes or causes more instability within the cloud and causes this rotation to continue. All these pieces of air that are trying to bubble up and get higher up, but these winds aloft are knocking them back down, causes this rotation. Finally, to step two here, sorry. How this rotation in the cloud starts to become more vertical is from the storm system being pushed into warmer and warmer environments, warmer and warmer surface environments. The more air you feed from below, the more warm air that's fed from below, and especially if the system's moving at a rapid rate, this warm air that's running into is going to take that more horizontal spinning tube of air and eventually tilt it to a more vertical fashion, as we see in step two there. And if all these things come together just right, that the rotation can become strong enough, the pressure can lower, and the funnel can come out of the cloud there. And I will have Jim Cantori from the Weather Channel do a little explanation here. He's got a really cool setup. They just built this machine at the Weather Center there that is like a virtual kind of diagram. It's like a 3D virtual diagram, and he explains this in a very quick way. But it's very cool to watch.
Here we are in the Weather Lab, and of course, we're very, very proud of this facility, and this is something we're just launching today. We are going to show you the anatomy of a tornado, okay? And think about this. We have all sorts of different sizes of tornadoes, right? You go from the funnel clouds and the weak tornadoes that you guys just showed to the F5 that hit Moore, Oklahoma on this date back in 2013. Horrible day. All right, let's talk about the anatomy of a tornado. It starts with a supercell, a rotating thunderstorm. But on these tornadoes, there is one thing that clearly stands out, especially when we look at radar. It is called a hook echo. And that hook echo is a little appendage on the southern flank of the storm. We know that these storms aren't flat. They're in the vertical, 40, 50, 60,000 feet. So let's pull this thing up and look at it. Because when you look at this big rotating thunderstorm, and as massive as it is, look at what's going on down here. Look at that tornado. So just a small part, but the most violent part of that supercell is right there in that tornado. So let's lift the base of this and talk a little bit about tornadogenesis, because a lot of the research over the past several years has gone into what actually kicks off the tornado from the supercell. Well, there's one thing that stands out. You can sometimes see this when you're in the field. It is called the rear flank downdraft. It's when the upper level winds get caught in the downdraft, they come through the backside, and if that rear flank downdraft isn't super cold, it can actually allow a tornado form, especially when you have on the eastern side of that warm, moist air. So warm, moist air, cool outflow on the backside of that, you see the rotation going on, and voila, we've got ourselves a tornado. Preceding a tornado, there's another feature we have to talk about, and you saw it on the video that we just showed. It's a wall cloud. It's the base of the thunderstorm beginning to lower, tremendous violent motion. Sometimes these whole wall clouds are rotating. Sometimes you just see the air coming up into the wall cloud. But when the wall cloud starts to produce a funnel, and whether that funnel is on the ground or not as a tornado, the problem is when you see debris on the ground, you know you've got a tornado. And the debris cloud is the last place you want to be, because within that, you've got trees, you've got homes, you've got cars, and sometimes you have humans. And that debris, of course, is being rotated around the storm and is eventually centrifuged out. In some of the stronger tornadoes, we see common features right around that immediate funnel. And that is upward motion right on the outside of that tornado, followed by inward motion, sinking motion on the inside. This is an amazing feat of nature, and no country in the world has more tornadoes than the United States. We average 1,300 per year. Sam, Jen, Anna Rittis, that's more than 10 times any other country in the world.
Wow.
Okay, so he went a little bit further and explained the whole downdrafts and updrafts that get caught up in these storms as well. Again, these are the most common. I wouldn't even say they're the most common. Maybe they are. Not quite sure. But they are certainly the most common as far as the violent tornadoes that we have. The different other types of tornadoes that we're going to look at, sure, they're all violent. They can all produce damage. They can all take lives. But these are the ones that produce the killers, are these supercell, what are called mesocyclone type storms. In other words, supercells, as we more commonly hear from the meteorologists on TV. We've all heard of water spouts, and everybody says, oh, it's just a tornado over water. Not really. It can be. A tornado can form, it can move over water, and it can become a water spout. It's really just a tornado over water, though. But true water spouts true water spouts will form differently than a supercell type tornado. Where do we more commonly see water spouts? This picture might give you a good idea. Where do we really see a lot of water spouts in our country? Florida, yeah, especially in the Keys and the very warm tropical waters. As I told you earlier, the Gulf of Mexico and that Caribbean area, it's very warm. And how water spouts form are a little bit different as far as the atmospheric dynamics involved. They really form from deep humidity and very deep heating at the surface, especially the surface of the warm ocean water. This intense rising motion can basically just spin these up if there is a storm cloud forming above them. This is a nice diagram that kind of explains how basically all you need is a lot of evaporation and a lot of rising warm air motion. and just some slight winds. And it doesn't even have, they don't even have to be. Typically in the Keys area, this is a diagram from the Florida Keys from actually a newspaper article I took it from. You don't really need winds out of the northeast or the east necessarily. It can be out of any direction. But if they're just right, and there's enough what's called vertical shear or different changes in the wind direction as you go higher up in the atmosphere, if all these play out just right where you have a lot of deep rising warm air and humidity, that's how these waterspouts form. And they form at the very beginning stages, usually the very beginning to middle stages of the parent thunderstorm cloud above them. And they're usually not supercell type thunderstorms. You don't get a lot of supercell type thunderstorm activity in the tropics. These storms develop and die out too quickly to allow themselves to gather and form such large super monster type storms. What happens in the tropics is that there's so much heating at the surface that the process of these popcorn thunderstorms, as you might have heard this term before, but these popcorn thunderstorms popping up in Florida during the afternoon pretty much every day in June, July, and August. That's a way of the Earth itself to kind of get rid of that excess energy that's being built up at the surface. It gets up into the upper part of the atmosphere where it cools and all that energy is released into the atmosphere, and the cooling effect from the storm itself and the rain and everything that develops kind of kills the process very quickly. But these things pop up and dissipate very quickly every single day down there. And waterspouts tend to form in these types of storms. And so does something called a landspout. I'll get back to these in a second. So does something called a landspout. It's basically a waterspout, but they develop in a very similar, if not identical manner, but over land. Okay. So the tropics, especially the Florida Keys area, you see a lot of waterspouts all the time. I get some really cool pictures here too. I'll be showing them, and some more video clips. But especially in July, August, September, when the ocean water is warmest, this is where you'll see the most waterspout activity down in like the Gulf of Mexico area and the Florida area. Anybody know where these guys were taken? Yeah, can you just tell by you can just tell by looking at it. You look out the window. Which way are we facing here? I haven't been on campus in a while. Want to face the lake here? This way? That way? Okay, thank you. It almost looks identical, right? Yeah, these were taken over Lake Michigan. I believe these are the ones taken near Racine just a few years back, maybe 5 years ago or so. I got a collection of pictures. I can't remember where they're all from exactly, but what's interesting about this is that now we think about the Great Lakes, they're not warm. The Great Lakes are very cold. Even the warmest temperatures of Lake Michigan in September are not very warm. It's not something you just want, I'm just going to go take a dip in the lake and go swimming. No, it's like even the warmest time of the year, when the water's the warmest of the year, you're still dipping your foot and being like, ooh, I don't want to go in there. But if that water is warmer than the air above it, than the atmosphere above it, these types of events can happen even in Lake Michigan and even in the Great Lakes as well. Interesting enough, this picture actually shows a family of waterspouts. Families of waterspouts or multiple waterspouts within view are very common, far more common than tornadoes over land are actually. And this map actually shows outbreaks or families of spots that have had outbreaks or families of waterspouts. Now I'm only showing this map not because of the outbreak or the family informational part of it, but it gives you an idea of the numbers of waterspouts that occur by each Great Lake as well. This is a very good representation of different data, actually. Lake Erie and Lake Ontario are the ones that get the most waterspouts. Anybody know why that is? They're shallower. They're very shallow, very good. And because they're shallower, they warm up much quicker than these deeper Great Lakes. As you can see, Lake Superior, the mother of the Great Lakes, the deepest, the coldest, gets far fewer waterspouts than any of the others. But we also are a very much of a fall, September-ish type seasonality when it comes to waterspouts in the Great Lakes. And that is because during our fall, the atmosphere can get cold very quickly. So some of those really cool days where we have some storm development going on over the Great Lakes, that water below it is actually warmer. Even though it's very cold, it's much warmer. And if you can still have that kind of steamy, rising warm air, warm humid air effect, even though it's cooler warm air, it's still enough to interact with the much colder air above it that's forming the parent storm cloud. This is actually a water spout, but it's a very small lake, as you can see. This is taken in Iowa. I believe this one is from Iowa. But this is just a very small lake. And this guy just happened to form right in a small lake. It could very easily have formed 100 yards over and been a land spout. So it formed under more of land spout conditions. But basically, land spouts and water spouts they form the same way. They form from an intensely heated surface, giving off lots of energy and lots of rising warm humid air into the atmosphere. Generally, a land spout, actually water spouts can be a little bit stronger. If you take a look at all of them over time and compare their averages, wind speeds and all that, land spouts are probably actually a little bit weaker, only because they lack the vast amounts of water vapor and humidity and moisture that gets sucked up into them as they do over warm bodies of water. There's a lot more energy, again, in evaporated, in air that has a lot of humidity and evaporation going on. There's a lot more energy being held in that than there is over drier land areas. But even a very humid, dry land area can still be heated enough and form what's called these land spouts. Now again, water spouts and land spouts tend to form underneath single-cell thunderstorms, not multi-cell or supercell type thunderstorms as we saw with the first type that we saw, the real violent killer-type tornadoes. Not to say that land spouts and water spouts can't get strong enough and be killers themselves. Even the weakest ones can. You certainly don't want to be in the way of any of these guys. But generally, they are weaker. They are not as wide in breadth. They are generally tall and skinny looking like this guy right here. And again, they form at the very beginning and middle stages of these thunderstorms developing during the deep convection or the very strong and large amounts of rising warm air that gets swirled up and caught within the winds that change as you go higher up in the atmosphere. You can get land spouts pretty much anywhere in this country, depending on the time of year, but the conditions have to be right. Okay? Generally, where you see a lot of land spouts are a lot of times you see them in the drier climate. You see them very commonly just east of the Rocky Mountains during the warmer parts of the year. Colorado, Wyoming, even eastern New Mexico tend to have a lot of land spouts formed during their midsummer thunderstorm. They're, again, kind of popcorn type thunderstorms or single cell thunderstorms that develop very quickly and dissipate very quickly. And yes, they do look like this. This isn't actually photo enhanced at all. I did a little research on this guy, and it's not photo enhanced at all. Speaking of these type of land spout tornadoes, these are more commonly found around the areas of the world that get tornadoes as well. Not that those supercell type thunderstorms and tornadoes can't develop in the parts of the world that we saw on that map early on in the slides. They certainly can, but these are more commonly the type of tornadoes that you find, the single cell thunderstorms that you find throughout the world. This gives you a good idea how early on in the developing stages of a thunderstorm a land spout can form. We've all heard of the Fujita scale, the F scale or the EF scale. Now it's called the enhanced Fujita scale, right? The EF scale. It's still basically the same thing, just slightly different with wind speeds and stuff like that. And generally they're weaker on the EF0, EF1, maybe sometimes an EF2 side of land spouts and water spouts. They generally don't get that destructive. You don't see F5s, F4s, F3s, generally. But this one gives you a very good idea of how early on in the development of a storm a land spout can form. I mean, look at it. I mean, this cloud is barely developed above it. And this is the cloud right here, not this one, not this one. It's this guy right up here. And you can see, unless there's a huge part of it over here that we're not seeing, this is pretty early on in the developing stages of that storm. But that's when these guys start forming, when the swirling up warm air gets sucked up into the storm cloud above it, so to speak. And again, you see a lot of these are more drier climate type events, but we also see them very commonly. You see land spouts very commonly form in Florida as well. And I had to show this because you got, I thought I saw some, there are palm trees. Okay, the image is just blurry. These are actually palm trees. I wanted to show this picture to show they actually form in the tropical climates as well. Now in Florida during the summertime when we get these basically daily thunderstorms, these popcorn thunderstorms popping up all over the place every day, usually between the hours of like 2 and 4-ish p.m. during maximum solar heating. Actually, the maximum solar heating of the most intense sunlight of the day is around noon or 1, depending on daylight savings or not, right? That's when the sunlight is most intensely hitting the Earth's surface. But the Earth's surface isn't warmest, and the atmosphere above it isn't warmest until a little bit later in the afternoon. There's kind of a lag effect between the most direct sunlight that we're getting and when the Earth itself is actually its warmest and giving off the most energy. That's why our warmest temperatures anywhere in the summertime are recorded usually around 2 or 3 in the afternoon, as opposed to right at noon during the maximum sunlight. It's a little bit later than that. But that's how these thunderstorms pop up too. They follow that same kind of lag. And that's when the land spouts that form within these thunderstorms are basically a result, again, of intense surface heating. But Florida has another unique setup. I'm not going to sift around looking for a map, but we know that Florida sticks out into the Gulf of Mexico, right, and into the Caribbean. It's a peninsula. You have winds coming in. You have sea breezes coming in from both sides of that peninsula. Where those winds meet inland and converge, further force up warm air into the atmosphere. When these winds come together, there's nowhere else for that air to go but up. They can't go down. There's ground there, right? Unless there's huge sinkholes that are big enough to suck all that air in. But this air has nowhere else to go but up. So landspouts are very common and very quick. They form very quickly and they dissipate very quickly in peninsular Florida during the summertime when these thunderstorms flare up because of that. And that's why that's another thing that adds to the frequency of thunderstorms in this region. It's not just the warming up of the intense warming up of the surface. It's these winds coming in from both sides of the peninsula, meeting inland and being forced upwards as well. Excuse me. The other type of tornado now. Hurricane tornadoes are very, very different. They are not like supercell tornadoes, although there can be supercells within these hurricanes that produce tornadoes. But we're lacking something in hurricanes that is very necessary for your typical monster supercell and mesoscale tornadoes to develop. And that's cold air. We have some cold air sinking from the very upper parts of the atmosphere in these large storm systems, but you don't have that surface cold air coming in that's necessary for tornado formation, especially violent tornadoes. But hurricane tornadoes can be far more violent than your land spout and water type tornadoes because of the different things, all the different things that are going on inside hurricanes. When hurricanes make landfall, they start to break apart. Hurricanes rely almost entirely on very warm ocean water. Basically, they do rely almost, it's not entirely, it's almost entirely. But once you go over land, the land is actually much cooler than this very warm surface water that they're coming from. That's feeding them through heat and energy and evaporation. Now you're going over land where it's not as warm and there's not as much humidity, there's not as much evaporative potential to feed that storm. So the storm starts to break apart. You'll hear your meteorologists talk about all the time how this northeastern quadrant of any hurricane, depending on its direction, say if this guy is moving straight west, this would be the area that is most likely to produce tornadoes. And now you have this band up here that is separating away from the main storm. That's because it hit land. As these storms hit land and start to break apart, these larger areas of basically continuous supercell areas start to break apart into smaller type supercell areas. But you have winds now, you have surface friction from the land is now playing an effect. Over the ocean, there's basically no surface friction, hardly at all, maybe a little bit from the waves. But once you get over land, it starts messing with the surface winds really bad and starts sending them in all different directions. Once you get this wind flowing in all different directions, it changes what's called that vertical wind shear, as we saw in that one diagram with that pole going up with the arrows going in all different directions. That is showing you change in wind direction with height or with altitude. At the surface level, when these hurricanes hit land, the winds start going all over the place. And this is what can spin off these very violent tornadoes within supercells that are part of a hurricane. So it's really, again, not as much as the cold air and the warm air coming together as much as it is just the severe change in vertical wind shears in all different areas that can spin these off as the supercells break apart when they hit land. What else is different about tornadoes within hurricanes as far as their characteristics? Talked about how they form and how they're different because there's just winds going all over the place that spin them off. But what else is different about them as far as where they're coming from and where they're going? where do most tornadoes come from and go to as far as direction? Basically west to east, southwest to northeast, northwest to southeast, west to east. Tornadoes come from hurricanes are moving east to west with the storm. So that's another different characteristic of these. Dust devils are not tornadoes. Some people think they are because they look like them. They do. But they don't touch the ground to a cloud. They touch the ground and they fade up into the sky. They're nothing more than intense swirling of warm air, kind of like how land spouts form, but without the parent cloud above it sucking anything up into it. Yes?
Well, on the dust natal, we had one about 20 years ago in Sheboygan, and I was at the Shopko parking lot at that time,
Mm-hmm.
and I saw it go down Superior Avenue.
A dust natal?
A dust natal.
A gustinado.
Gust-
That's my second myth bust right here. Gustinados are not tornadoes either. They're big blobs of cold air that come sinking out of the cloud. Think of big cold air sinks, right? These storms and the rain and everything that's going on inside of them produce big pockets of cold air that eventually, it's too cold and it's too heavy. It just can't stay suspended up in the air anymore. It just sinks and it hits the ground. It has nowhere to go, so it goes whoosh, and you get all this air moving everywhere, right?
Huge, and people that were along
But
at North Point Drive said they saw gulls being sucked into.
Sure. I mean, you can have a swirl, sure, but it's not a cloud connected the ground to the parent
I
cloud.
know what you mean.
It's a swirl from a surge of air coming from it. If I brought a big fan in here and brought a bunch of confetti, you would see some swirls of confetti here and there. That's what a gust front or a gustnado basically is. It's just swirls from large areas coming out, and that happens naturally. All sorts of swirls happen from wind blowing. And a gustnado is nothing more than that with a little bit of condensated air, cloud air, kind of got sucked up into that. But those are not actually tornadoes. They're just kind of whirlwinds out ahead of the front of the storm.
But I'm just saying, can it have some effect like a tornado?
Well, it spins like one. It depends on how strong the gust is. And usually when it starts swirling, it starts to lose its strength real quickly. But if it just started, I mean, who knows? And I'm sorry, but Sharknadoes are not. They don't happen either. So. I wish the internet was working because this one you'd see an interactive of, okay, getting into seasonality now. We know that, again, I've been saying that tornadoes can happen year-round, but we know from, if you're here because you know a little bit about them already and you know that our tornado season, as the media likes to call it, is basically springtime and early summer during the real rapid changing of the atmosphere in our country during that time, during the different air masses and their characteristics and how they're warming up and cooling down, or pardon me, how they're warming up very quickly this time of year. This map actually goes from every day of the year and shows how the potential areas get higher and lower and how they change geographically through every day of the year. But this graph here will show you, okay, so April, May, June, this is where we get the most of our tornadoes. We have some outliers here and there. Again, this is by day as well. Be careful. Some of these include data that is part of outbreaks of tornadoes, huge storm systems rolling through that can produce dozens, if not 100 or more tornadoes. If anybody was around in the 70s, you might remember the super outbreak that happened in 1974, 1973. It was basically all across the country from a storm system from basically Ohio and Pennsylvania all the way down through Texas here. And over 2 days, 148 tornadoes were recorded. And that was in the 70s when our technology sucked. So now with our technology and everything and all the trained storm spotters and everything we have now, there were probably 148 more that were out there that we never recorded, that nobody ever saw, and that our technology never picked up. But be careful of tornado data, because when it includes outbreak data, you can have these statistical outliers, as you see right here, in certain times of the year. But yeah, our seasonality is, as far as when the most tornadoes occur, it's also our most active severe weather season as well during the change of the season. The northern hemisphere is largely landmass compared to the southern hemisphere, which is largely ocean. The northern hemisphere warms up very quickly starting in about March and April. Basically starting in December. Once you get right around to Christmas, now the amount of daylight hours increases slowly up until June 21st or so, right? Think about all that extra energy that's piled up every single day after the shortest day of the year. The more sunlight you have, the more energy is going to be given off or be generated at the Earth's surface from the longer exposure to daylight, day by day by day. That increases. By the time April comes around, and now the sunlight, the angle of the sun in the sky is higher and more intense. The higher the sun is in the sky, the more directly it hits the surface, the more energy it's going to produce at the surface and the warmer temperatures you're going to get. That's why we have our seasons, at least in our latitudes here. But throughout the year, you can see from month to month here how the activity increases. And again, it is strictly related in a sense to the amount of daylight we're getting and the intensity of the sunlight that's hitting the surface and how warm things or how warm it can heat up the surface. The more you heat up the surface, the more evaporative and energy release capabilities the surface has, and that interacts with the cold atmosphere above it. So you can see not only do the numbers increase, given by the larger amounts of the dark reds here, but you can see the geographic shifts as well throughout the years. So April, May, and June, April it's starting to shift out from the south and getting into the Great Plains here. By May and June, our Tornado Alley region is in full effect, right? May and June. Tornado Alley being basically northern Texas all the way up through the Great Plains states here. And now July and August they start to taper off because we start getting the drier conditions in August. When you have drier conditions, you have less evaporative potential, less thunderstorm development potential. But you can see by July, a little bit after our maximum daylight time of the year, June 21st, is first day of summer, we have the most amount of daylight and the strongest angle of sunlight hitting the surface. You see by July, now this lag is starting to kind of reach up to the north where it's finally starting to warm up in this region. And this is why tornado season is highest in our northern plains versus our southern plains, which is like a month or two earlier. Okay? Same thing in Wisconsin. We probably get more tornadoes in Wisconsin in our later summer months than we do in our earlier springtime season, because let's face it, it's still really cold here. Who was at Summerfest last year wearing their jacket? You know, if you went down to Milwaukee for Summerfest, I mean, it can still be very cold getting into later June. Okay, so now let's pay attention to some other areas, not just our Great Plains where we have our killer type tornadoes, our supercell and mesocyclonic tornadoes. You still have plenty of landspout type tornadoes forming in this region all times of year as well. Single cell thunderstorms can pop up most times of the year that it's warm enough. And you get a lot of these F0, F1 type single cell landspout type tornadoes forming all times of the year. But really this key active tornado season of April, May, June in the Great Plains is where you get the real severe type weather, the real killer type supercell thunderstorms. All right. Yeah, I wish that interactive would work. It makes this so much more interesting to look at instead of going through slide by slide. But it does give you an idea. Now in our cooler season, our cooler times of the year, October, November, December, January, got to go back to January. You see in our winter months, basically, our severe weather is not confined to the south, but it's certainly more prevalent throughout the south. And why is that? Because it's warmer down there in the south. This is still area is still dominated by subtropical high pressure throughout the year. It's definitely cooler than it would be during the summer months, but nonetheless, this interaction between warm, humid air and cold, dry air to the north can still give you plenty of storm activity down south. If you're here watching me tonight, you wouldn't be surprised if you were watching the news and it was January and there were some killer tornadoes that ripped through Mississippi and Alabama and Florida. Wouldn't be a surprise to you because you know enough about how our atmosphere works, and this is where our warm weather is during that time of the year. But there are other times of the year now, as you get into our summer or spring and summer months, that warm air is more widespread. The more widespread that warm air is, the geography of tornado potential expands as well. Now there's some other things that affect tornado frequency as well, and lecture I gave here a couple of years ago was on the effects of El Nino and La Nina on our winter weather here in the U.S., especially down in the southeastern part of the United States. The effects of El Nino and La Nina on severe weather can be profound. What El Nino is basically, and what La Nina are part of a normal climate setup that we have in our equatorial Pacific. Equatorial Pacific meaning along the equator, about 4 or 5 degrees north-south latitude from the equator, so within the very equatorial region, the very tropics itself, from South America all the way over Australia. This whole equatorial Pacific region, basically it's its own climate system. But it's set up by the ocean. Warm sea surface temperatures lie to the west, and the cooler sea surface temperatures lie to the east. During El Nino, these warm sea surface temperatures start to spread eastward. And this disrupts all the normal type of climatic and weather activity that goes on in the northern hemisphere Pacific to the west of us. And us in the middle latitudes where we are downwind from the Pacific. We get a lot of that humidity and water vapor, evaporative potential from the Pacific blowing into our continent. But when you shift the areas of storms within the Pacific, it disrupts that whole system. It also disrupts the average positioning of our jet stream. So during El Nino, we will see this jet stream, again, which is kind of the border between our warm and colder air masses and where these low pressure systems tend to develop and we're basically called the storm track. This jet stream position gets sucked down farther to the south because of the changing and the change in positioning of all the storm activity going on down in this area right here. So this guy will tend to be farther south than normal, more often than normal during an El Nino winter. Whereas during a La Nina winter, which is nothing more than a normal condition but stronger normal conditions, that tends to keep the jet stream higher up in latitude or farther north throughout the United States. It also tends to make it do these weird what are called undulations or wave type of effect. And we get a lot of severe weather in our nation's midsection right here during the wintertime, during La Ninas. But during El Ninos, when the storm track is more often than not shifted to the south, we tend to get more severe weather and more rain down south.
Is it the pattern we're in this year? Why are we seem to be getting these constant dips of that cold
I don't
weather?
know. I haven't looked at our El Nino, La Nina conditions since the last time I did the lecture here on that 2 years ago. It was an El Nino winter that year. We can look at that when we're done, though, and I'll have an answer for you then. But we tend to see a lot more severe weather concentrated down south during the wintertime. Now, these effects are really only important during the winter because during the summertime, we're already very humid throughout most of our continent. But during the wintertime, where we have cold air dominating or colder and drier conditions dominating most of the country, most of the continent, now you're throwing an influx of additional humidity, additional water vapor, additional atmospheric moisture into our atmosphere here that normally isn't there. And this is what really throws things off and causes more rain and more severe weather to happen, especially along where the storm track is or where the average jet stream positioning is. That's where you're going to see more rainfall or even possibly snow more often than you would have during non-El Nino years. It also brings the cold air from the north farther south. Again, that jet stream separates the colder air masses from the north to the warmer ones to the south. So if that average position is farther to the south, it's bringing all that cold air with it behind it. So you're going to have colder temperatures down in this region as well, and certainly more rain and possibly more severe weather. So that's another thing that's another component to our severe weather and to the physical geography of this country that affects not all areas of severe weather, but especially where you have higher potential and higher probabilities of severe weather and tornadoes. Does anybody recognize this one? Anybody recognize this tornado? Little northwest of here, about 2 decades ago. It was an F5. Nope, that is southwest of here.
That was Oakfield.
Oakfield, there you go. This is the Oakfield tornado, yes. All right. I'm almost done here. I just want to go over a few myths here and kind of, a few more myths and a lot of things that are misunderstood by our public. Hopefully this link will work this time, maybe not. I'll have to try to remember all 13 or so that were on this page. I won't. So any other questions while we're waiting for this to fire up? Your question earlier was?
The barometric pressure dropping or rising when a storm is like
Okay. Well, I'll get back to that slide, and I'll show you where you can expect to see rising and lower pressure throughout that. All right. Nice picture, huh? They copied me. All right. So, yeah, because there is this news team that recorded the whole thing getting out of their van. They were basically being chased by a tornado. They could not, they kept driving and driving, and this thing was right on them. So they stopped and got out and went underneath, up that angled thing in an overpass, and they waited it out, and the camera was rolling the whole time, and the winds kept changing different directions, and some of them were almost blown away by it, but they weren't. And somebody told them being under that overpass saved your life. They just got lucky. Being under an overpass is not a good idea because it's got that funneling of the winds that the winds are already very strong. But we know that walking through like a downtown area on a windy day, it tends those winds tend to be funneled and are even stronger. Same thing on a freeway overpass. Not a good idea. You're increasing your chances of being sucked out by it. Tornadoes never strike the same location twice. That's not correct. There's a town, and I forget the name of it, but it's in, I think it's Missouri. And they were struck 3 years in a row by a tornado. And it was in the early 1900s, like 16, 17, 18, something like that. But I was reading about it once, and this isn't an uncommon thing where tornadoes can hit the same locations multiple times in not too long of a time frame, too. Big cities and taller buildings protect from tornadoes. No, they don't. Think about all the stuff that we looked at in the early slides and how you have continental size air masses necessary for all this storm activity to start taking place in a more localized regional area, and then get down to the specific local area for a few tornadoes to pop up here and there. It takes oceans of atmospheres to come together to form tornadoes. So a little bit of some buildings in a city interrupting a little bit of the airflow at the surface is not going to do anything to stop a tornado. And large lakes, no, living by Lake Michigan does not protect you from tornadoes. Why the hell do you think we have water spouts all the time? Lakes do not protect you from them either. It
still has a profound effect on weather coming.
Sure. Well, storms, as they pass over the lake, they start to dissipate. But being on this side of the lake, yeah, they start to dissipate because of the cold air. You have cold air not giving off evaporation, feeding it anymore. Fine. But as far as being next to the lake, that storm is still going to be very strong until it gets several miles out into the lake. So being on this side of the lake, it's not as much. There's no effect, or there's no protection being either living on the lake or being 10 miles inland or less. There's no effect. Maybe on the other side of the lake a little bit. But generally, the landscape, the differences between the landscape and the water on the other side of the lake can actually help to fuel up and fire up thunderstorms immediately inland as well. I don't have time to get into that. If you want to stick around, I can explain that. But it's more of like a sea breeze and land kind of interaction. But if you want to stick around, I can explain that. Mountains, ridges, river valleys, all that, they don't stop tornado development. Although higher elevation areas are not as conducive environments for tornadoes, they don't necessarily stop them entirely. The southwest corner of your basement. Basically, go to the middle part that you're most protected in. In corners of your basement, in corners anywhere where there's wind going on, that's where debris gathers, or in the corners. So if anything, you want to be under something solid, preferably somewhere more in the middle and at the lowest location in your house. The shape and size can tell you how strong it is. Sometimes, you see a big marching mountain-sized tornado coming your way. You're not thinking that it's some cupcake that's just gonna, blow down a few leaves off the tree and that's it. But at the same time, they're not entirely indicative of how strong a tornado can be. Even those small rope-thin ones can be very strong. All right, mobile homes attract tornadoes. No. Mobile homes attract news crews when they get damaged by tornadoes. That's what it is. Number of tornadoes has increasing because of more favorable conditions? No. Population is increasing, so there's more people out there spotting them. Technology is getting better, so we can track them better. Yeah, I mean, that's basically it. Florida used to be like ranked number 5 in the number of tornadoes, average number of tornadoes per year by state. It used to be like number 5. Now it's like number 2 or 3. Why? Because population has increased in Florida substantially since the advent of air conditioning and seniors flocking down there to live. Yeah. But really, I mean, inland Florida is still very sparsely populated. There's probably a lot of landspout type tornadoes that occur there, especially during the summer months, that nobody ever really sees, and that might be too weak to even be picked up by our really sensitive technology. But population increase alone is one of the big things that has helped us record and record more numbers of tornadoes over the years, but the technology as well. And no, global warming isn't really doing that, not that we know of just yet. Okay. And, okay, a few landspout myths. Landspout, yes, they're tornadoes. They're weaker, generally, but they're still tornadoes, and they can still flip over a mobile home and your car. They can still tear the roof off your house if they're strong enough. There's not anything you can just stand there and let it just go right past you. I mean, they're certainly a danger still. And certain tornadoes, again, especially the landspout and single cell type tornadoes and waterspouts that form, don't necessarily always have this wall cloud that drops out of them. So you don't always know that they're coming. Where you can see those, the first signs of those are usually the swirl at the ground. One interesting thing about landspout and waterspout type tornadoes is that they kind of form from the bottom up. They need that parent storm cloud ahead of them, but they start swirling at the base and start connecting to the ground from the ground up, versus our supercell and mesocyclonic tornadoes, which always have that kind of, looks like a finger kind of coming out of the cloud, and it starts getting bigger, and eventually it touches the ground. There is differences in the way that they form that way. But the first evidence you can see of land and water spouts is the swirl at the ground level. All right, that's what I have so far. I was going to do a little bit more tornado safety, but I think you guys should all know most of that stuff by now. So, questions? Okay, let's get to that first one that we had here on our wave cycle. Think of this guy. Okay, we have a low pressure system here, right? Cold air is moving in from the northwest, flowing to the southeast. Warm air is feeding into this system and moving basically from the southwest to the northeast, right? Where you have rising warm air, the pressure is going to be lowering. So where's my pointer here? So along this warm front here, it's warming up in this area, and this air is being lifted over the cold air ahead of it. That's going to give you lowering pressure right there. And say this storm is moving straight east. This L right here is moving straight east. That's the center of the system. It's moving straight east. This guy is going straight east. Anywhere along this front, the pressure is lowering. Anywhere along ahead of the front here, this cold front, the pressure is also lowering. When you're forcing warm air up into the atmosphere, you're forcing it up, the pressure is lowering. Basically what atmospheric pressure is how heavy does that air above you feel? Is it pressing down on you, or is it lifting up and becoming more buoyant, becoming lower pressure? If warm air is being forced up in any given way, the pressure in this area is lowering because the air is rising. All around the rest of the storm, where the air is colder, you have increase, well, not necessarily right in here, but especially behind this cold front. Now that the cold air has moved in and you're getting colder air behind it, now the pressure is starting to rise. Anywhere behind this cold front, the pressure is starting to rise. Now this L here, the center of the low pressure, is the lowest pressure in this whole system. The pressure increases as you go farther away from the center of the low pressure center, right? So not only is the low pressure center moving away, so the pressure is naturally rising, but you have cold air behind it. Cold air tends to stay at ground level unless it's being forced up somehow, and it's not in this case. So cold air and sinking motion from the upper atmosphere gives you higher pressure. So now after the cold front here, you have rising pressure. So anywhere where air is being forced up right ahead of the cold front and along and within and along the area of the warm front, where you have lifting of the warm air, is where you're going to have the lowest pressure. Does that help? Okay. Have you had physical geography here?
No.
You should take it. You talk about this stuff for, you'll do some lab exercises actually on this stuff. It's really neat. They bring, it's probably all interactive on the computer now, but they used to have these little cards that you would slide out, and by frame, you'd see how the low pressure system changes as it moves along and matures and then dissipates. It's very old school type technology, but it's very effective in teaching it. And another question. Whose question did I have?
Lake effect.
Yes, okay. I just need a US map here. That should work instead of blobs away. Okay. All right, so.
I've seen, as storms come from the west, I've seen them look really,
Yep, really menacing, and then they get over this cold lake and they start to disappear.
because the energy is taken on from the
Right,
cold
the
air.
warm air and all the evaporation is now over. Now, again, if the lake water is very cold, the air right above it's going to be cold too. It's just through conduction or through the touching of them, the air is going to be cooler, so it's not going to feed that storm as much. That's true. However, think about this. Even on our side of the lake, but especially on Michigan's side of the lake, that air sitting over the lake is very cold. The air over the land is warm. Why? Because that sunlight is hitting the land. Dry land warms up and cools down very quickly. So as that land warms up and that air starts to rise, now something needs to flow in to replace all that rising warm air. Where is that going to come from? It's going to come from Lake Michigan. All that cold air sitting right over the lake is going to flow in to replace all that rising warm air. That's why it's so breezy along the lakefront on really warm, sunny days. If you're near the lakefront around here, Lake Michigan, it's probably pretty windy. If it's 90 degrees and it's clear out and the sun is shining, it's probably pretty windy and a nice cold wind coming off the lake. That's the cold air rushing in to replace all that rising warm air. Something has to flow in to replace that. That warm air just doesn't rise and now there's nothing because we'd all suffocate. But there's that cold air over the lake that stays low to the ground because it's cold. Get cold air sinks, warm air rises. That rising warm air evacuates and something has to come in to replace that. And that's what those cold winds are coming off Lake Michigan. Now you get that on the Michigan side here. You have a nice clear summer day and it's warm and humid, and all of a sudden, clouds start to pop up and you start to have this cold air flowing in, basically exacerbating the whole process, forcing that warm air over the land up even quicker. Kind of like how we have this sea breeze effect in Florida during the summertime. We have those thunderstorms pop up, not only because of the intense surface heating, but all that cooler. Now it's still warm, but it's cooler than the warm air rising over the land. It starts to flow in to replace that. And when they collide, when they converge, they force that warm air up into the atmosphere even more so, and basically intensify the effect. Same thing can happen along our lake shores in the Great Lakes. So yes, a storm system moving from the west to the east here can dissipate over the lake, but it can easily fire right back up again once it gets to the other side over land. Yes?
If you go forward 2 slides to your water temp slide over the Gulf, there's something there that struck me as being really counterintuitive. I'm curious about it. I would think that the waters would be warmer where they're shallower, and it seems like it's the opposite, the surface temps. Because it seems like they're going down as you get closer to the coast.
Right. Okay. Well, this is March, so that has a lot to do with it. If this was June, it would probably be opposite. These temperatures here in June would probably be pretty much the same, maybe a little higher into the 80s, but these would be in the upper 80s very easily because you're right, it is more shallow. But we're in March here, so we're just getting to the equinox part of the year where the effect of the more direct sunlight is just starting to really take effect in our hemisphere. So give it another month or so and they probably will be warmer. At first, when I looked at this map, I thought this was a sea surface temperature anomalies shading, meaning that they're departures from the average or they're differences in what the average is. These are actually the water temperatures themselves, and the shading is showing that as well. But yeah, once we get into our maximum warm part of the year, you would see warmer coastal temperatures. It's not always like that, though, because it depends on how the water movement is as well. Remember, we have a very warm ocean current coming in. I didn't talk about this. But the Atlantic Ocean current coming along the equator is riding up and along the east coast of our continent. So it's bringing all that warm water with it. A lot of that is getting into here. Okay? So that's what's keeping this warm during that time of the year. Now, with the less direct sunlight, the reason this is so warm is because a lot of the mixing and the current, the Atlantic current feeding into there. But where it really starts to warm up is during our later spring and summer months. Yeah.
So is it true, I've heard that huge acreages of cornfields in Iowa and Nebraska can actually make their own thunderstorms by the moisture given off by that corn?
Clouds, yes. They can help produce clouds. They can't produce. There is a class called agricultural meteorology, and it was at I think I saw it at either UWM or at Madison's meteorology department. I always wanted to take it because I wanted to know a little bit about it. I did some reading on it, and it can affect what's called micrometeorology and microclimatology. But it really doesn't affect our large-scale synoptic type weather systems. You might get a small cloud or two pop up here and there over large acreages or say maybe even hundreds of square miles of agricultural fields. Yeah, because we're putting in water in a normally you talk about the Great Plains area like Nebraska, let's say, right?
Nebraska and Iowa
Sure.
are classic places for that.
Nebraska, Kansas, Oklahoma, we're talking like semi-arid climates, not desert, but not a humid continental climate like we have. So they're kind of in between. But on large scales, and you're adding a foreign crop that doesn't belong there, and it has to be watered a lot. And there's a process called evaporation that we all know, but living things, including humans and animals, but also any kind of ground crops, anything, trees, anything, has something called evapotranspiration. And that's a process of water evaporating out of a living organisms. When we breathe, we respirate. We're breathing out a little bit of water vapor every time we breathe. We evapotranspirate when we breathe. But crops and trees and all that do that too. There's a little bit of water that is evaporated and sucked out of living organisms. And that will put more moisture or more humidity into the atmosphere in localized areas. How much of an effect that actually has on the actual weather, I'm not quite certain, but I don't think it's very profound. It might, like I said, it might develop some clouds here and there, maybe a little bit of wind shifts, and maybe a quick pop-up rain cloud. I don't know.
Isolated storms. is what
Maybe.
they say that
Maybe, but it certainly wouldn't produce a supercell type storm, and it's probably wouldn't even produce.
Isolated
Yeah, but
rain showers.
rain showers and stuff, yes. As far as even like a single cell, like landspout producing thunderstorm cloud, I doubt it would even have enough to do that. I might be wrong. I'm a geographer, not a meteorologist, remember. This is my specialty, is the atmosphere. I like to tell people that. When I don't know something, I'm like, well, I'm not a meteorologist, you know. Anything else? Anyone? Yes.
Kind of off the wall. You may very well not have an answer for it at all. That has nothing to do with tornadoes. But when I lived in Florida, we lived in Gainesville for several years. And in the summertime, about 4 o'clock in the afternoon, just about every day, you get rain on a clear blue sky, even if there were no clouds. How's that happen? Is it just the humidity is so...
It's so humid, and something in the air is just right that it allows it to condense. And it's not necessarily rain, but it's like you feel sprinkles, right?
Yeah.
You just felt sprinkles.
Well, sometimes there's actual, like, raindrops.
Yeah, okay. But not like heavy, not a deluge of rain or anything like that. Just enough rain to feel, though, right? I've only experienced that one time. I was in my 20s. I was in the middle of a baseball game, and it was middle of the afternoon, 2 in the afternoon. It was hot and humid. And all of a sudden, I felt sprinkles, and everybody was like, is it raining? And it was sunny. It was clear. But it was just so humid, and something happened in the air where it allowed the water vapor to condense and just form droplets enough to be able to feel them. And it's not like you felt a drop and then like the water splattered and stayed on you. It wasn't even like that. It's like you felt it, but it wasn't there anymore. It was almost like phantom rain. So you could actually see yours. To me, that's just a quick condensation of the humidity, but how exactly that happens, I don't know. I've never really looked into that. I could. I'll email you. Actually, now I'm interested in this, and when I have a better explanation, I'll email it to you. Yes, ma'am.
I don't know if this was similar, but years ago probably even before the 1850s, it would seem like it would be sunny, and then there would be clouds, more cumulus type, and then it would just like you said, it would rain around 3:30, 4 o'clock. So many days during the summer months.
Around here?
Whereas now the weather is completely different.
Are you talking around here? Around here?
Yes, the Sheboygan. It was like you just knew it was going. It was during the summer months, and you just knew it was going to rain about that time. And Mom would say, "Come on home because we're going to have some rain," and it would.
We're not actually. We here in Wisconsin are actually not strangers to the same type of conditions that Florida has throughout their summer months, where we can have just a nice, really hot 90, 95 degrees, very humid, and it's sunny. And then all of a sudden, a bunch of clouds start popping up, and it rains real quick. It's like it squeezes out that extra humidity in the air, and it squeezes out that extra energy and cools things off just a little bit enough, and then things resume back to normal within an hour. We're not strangers to that here either. Now, that's not our climate. We don't have that regularly here, but we could easily have that those conditions for a few days to up to a month or more. Around here. I remember, I don't remember exactly when. It was sometime when I was in college or shortly after, but we had a whole month where we basically were like Florida for the month. That subtropical high migrated up to the north, and it basically sat over us in our region here for like a month, and we had the hottest, most humid summer ever. And we had that same type of Florida weather. Basically every afternoon we had some thunderstorms, and I thought it was really neat. But we will get those conditions, but they normally don't last real long. We might get them once or twice or 3 times. They might come and go. They might come and sit over us for a month. They might never make it up to us at all. There have been some summers recently where our high temperature for the summer was 89 degrees. And we didn't experience that type of few days where we could easily have some afternoon thunderstorms pop up. Generally, the type of weather activity, especially storm and rain activity that we get, are along the lines of the frontal and low pressure type systems.
Another question I had was, which one of those La Nina, El Nino thing are we in this year?
Let's find out. If the internet's working, let's find out.
Probably one of the weirdest winters I can remember here.
It certainly was. This winter was certainly. Well, there wasn't a lot of snow. The El Nino. So the effects that we're supposed to get. The averages that we get in our El Nino winters here in Wisconsin were generally more snow and generally a little bit warmer. That winter we were a little bit warmer and we hardly had any snow, which was really strange. But there were some other climatic variables that came into play that basically disrupted the effects of El Nino that winter, which I found really odd because they had to have been the perfect intensities because that was that super mega Godzilla El Nino we were supposed to have that winter. And here I am all excited because that's what I did my master's research on and my thesis on and this and that. I'm all excited like, yay, we're gonna see all this stuff I've been talking about all the time actually happen, and it's gonna be like, amplified, and it totally wasn't. It was a total dud. I was so disappointed. Now this year we could just be under a neutral phase of El Nino where we're not El Nino and we're not La Nina. It could be neither, and we just had a strange winter. Winter weather is very. It's it's hard to understand.
Struggle to predict it a lot more in the winter than he does in the summer.
Say that again?
The weatherman seems to struggle with predicting the weather more in the winter than he does in the
Yes. Winter weather is. it's tough because we have very cold conditions in the north and still pretty mild and warm to the south. In the summertime, things tend to be a little more evened out that way. So things especially after the spring months, things tend to stabilize. July, August, September, October, November, very easy months on the weather. But then, yeah, come December and after that till spring, it's tough.